Okay, Physics 20s, welcome to your first experience with a recorded lesson. And it's on Newton's second law of motion. So you need to be in your notes booklets on page 10. And you should have highlighters on your desk. If not, you can send somebody from your desk up to the over there where the highlighters are by the water cooler and grab a cup of highlighters. So what we're talking about today is Newton's second law, which is just sort of putting into words and equations information that you would have found out in the lab that you did yesterday. So the outcomes that we're covering today are apply Newton's second law of motion to explain qualitatively, so that's with words, the relationships among net force, mass, and acceleration, and apply Newton's laws of motion to solve algebraically linear motion problems in horizontal and vertical planes near the surface of the Earth, ignoring air resistance. We're just working with horizontal today, though. So both of those outcomes are green. Okay, so those are both comprehension and application outcomes. What you need to be able to do to show me you can meet those outcomes is state, which is yellow. So just stating Newton's second law and applying Newton's second law. That applying is green. So state and apply Newton's second law of motion to explain qualitatively, again with words, the relationships among net force, mass, and acceleration. Solve for any variable, and acceleration is equal to F net divided by mass, and acceleration due to gravity is equal to force of gravity divided by mass. So that solve is green, because anytime you're calculating, that's green. Define normal force, that's yellow. We talked about that a little bit already. Relate standard international units to physics, the physics quantity of force, and that force is in newtons, or kilogram meters per second squared. State that the gravitational force acts on an object at all times, when rising, at rest, and when falling. Or in other words, gravity never sleeps. There's always gravity, you can't escape it. So that's yellow. Determine the normal force for an object at rest on a horizontal surface, and determine the normal force for an object on a horizontal surface when an external force is applied. Those are both green. Okay, so moving into the lesson, and I'm trying to speak slowly. I have a tendency to speak fast when I'm making videos, but you can stop and start the video as much as you need to catch up on what's going. So just pause can be hit at any point if I turn the page too fast or if I move the page up and down too much. So Newton's second law of motion says that when an external non-zero net force acts on an object, the object accelerates in the direction of the net force. The magnitude of the acceleration is directly proportional to the magnitude of the net force, and it's inversely proportional to the mass of the object. Okay. So putting that into kind of proportionality statements, acceleration is directly proportional to the net force. So what that means is a change in the net force provides the exact same change in the acceleration. If you double the net force, you double the acceleration. If you half the net force, you half the acceleration. And then it's inversely proportional to the mass. So if you increase the mass, you decrease the acceleration. So if you double the mass, you're going to decrease the acceleration by a factor of 2. If you quadruple the mass, you're going to decrease the acceleration by a factor of 1 over 4. Just in other words, if we can say this just says if F net increases, acceleration increases. And this says if if mass increases, then acceleration will decrease. And remember that we had mathematical relationships or graphical relationships that we could show at the beginning of the semester that showed this. So this is a direct relationship here that I drew with the straight line, the linear graph, and this is an inverse relationship with that curved line. What this all leads to is the formula for Newton's second law, which says that acceleration is equal to F net divided by mass. Okay? Where A is acceleration in meters per second squared. F net is net force in newtons, and M is mass in kilograms. Okay? And this formula is on your formula sheet. Okay. What this formula basically says is that when a force is exerted in the same direction of movement, the object speeds up. And when a force is exerted in the direction opposite of the movement, the object slows down. And again, I'm going to remind you, you can hit pause here to catch up if you want. I'm just trying to make the video as short as possible so it doesn't take up as much space on my hard drive. So I'm going to move the page ahead now. Okay, and we'll just do some examples with Newton's second law. So we have a net force of 18.0 newtons acts on a 15 kilogram object. What is the acceleration of the object? So this is a pretty straightforward formula. And so for of all lessons for me to have been absent for, this is actually pretty straightforward and easy, and you guys shouldn't have any difficulty. So F net is 18.0 newtons north, and the mass of the object is 15.0 kilograms. And we'll make north positive and south negative. When we're just solving simple questions like this, where we're just using a single equation, we don't have to worry about a free body diagram. We have the net force. We don't have to find the net force. If we're trying to find the net force from a bunch of other forces, then we do have to include a free body diagram. But in this case, we're just using acceleration as F net over mass. Next class, we're going to kind of combine the previous lesson we did finding net force with this lesson finding acceleration. Then we do have to be careful about free body diagrams. So 18.0 newtons divided by 15.0 kilograms is going to give us an acceleration of 1.20 meters per second squared, and that's north. Okay, example 2, we have a 64 kilogram object accelerates uniformly from rest to a velocity of 16 meters per second east. If the object's displacement during that time is 50 meters, what is the net force during this acceleration? So we want to find F net. So we're going to be using F net equals mass times acceleration to find F net. We know that the mass of the object is 64 kilograms. We have it accelerates from rest, which is 0 meters per second, to a final velocity of 16 meters per second in a displacement of 50 meters. Sorry, that occurs over a displacement of 50 meters. So what we don't have here, like we've got mass, but we don't have acceleration. So we're also going to have to find acceleration. And we find acceleration using a kinematics formula with these 4 variables here. So we're going to use Vf squared equals Vi squared plus 2AD. Okay, and then you start to see where sometimes those kinematics equations have to be used in dynamics questions. So we're trying to solve for acceleration. We want that guy by itself. So we're going to have Vf squared minus Vi squared divided by 2 times d. That gives us the acceleration, which is 16 meters per second squared minus 0 meters per second squared divided by 2 times 50 meters. And just make sure when you put that in your calculator that that's in brackets, and that is 2 if you put in the 0 squared, although you don't need to. So the acceleration you should get here is 2.56 meters per second squared, and that's east. So now we know the mass was 64 kilograms, and we're going to use the acceleration we found, 2.56 meters per second squared, and that's going to give us our net force, which comes out to be about 163 newtons, but with sig digs we want 1.6 times 10 to the 2 newtons, and that's east as well. I neglected to do my directional justification, make east positive and west negative, so I was keeping everything east positive. Okay, so a type of question you also need to be able to do is what's called a proportionality question. Oops. So this is working with proportionalities. These are blue level questions or standard of excellence questions, if you want to think about it that way. And what it involves is it involves figuring out if, like, you're not really given a lot of data. You're not given values for all the variables. You're just given, in this case, a value for acceleration. And then you're told that the force is going to change by a certain factor, or the mass is going to change by a certain factor. And you want to know what change is going to happen in the acceleration. So what we have here is the acceleration of an object is 24 meters per second squared. So that's our old acceleration. That's what I'm calling that, is my old acceleration is equal to 24.0 meters per second squared. And so part A here, I want to know how my acceleration is going to change if I increase my net force by a factor of 4. So my force, F net, is going to become 4 times F net. And this goes back to what I stated at the beginning when I introduced the formula, that acceleration is directly proportional to F net. So whatever change you make in F net, where we're going to times it by 4, you have to make the same change in the acceleration. So then that means my new acceleration will be 4 times 24.0 meters per second squared, which is 96.0 meters per second squared. That one's pretty easy. Any change you make to net force, you make the exact same change to acceleration. And I want it, this is not solving for a variable. So it's not to get rid of the 4 on the right hand side, I have to divide both sides by 4. That's not what we're doing. There's not an equal sign here. This is a proportionality. It is not an equation. Because we're not working with values for variables, we're working with proportional changes. It's a little different. So changing the net force and finding how that changes the acceleration is pretty straightforward. Mass is a little bit more tricky because the relationship is inverse. So for acceleration, it's inversely proportional to mass. So whatever change you make in mass, you make the inverse change in acceleration. So I have mass. Mass is becoming mass over 3. So I'm dividing mass by 3. Okay? So what I'm doing here is to find my new acceleration. If I want my new acceleration, that's going to be 1 over m over 3, which if I simplify that becomes 3 over mass. So what I've done on this side is times by 3. So what I have to do on this side is times by 3. So my new acceleration, because I'm making my mass 1/3 smaller, my acceleration becomes 3 times bigger because it's easier to accelerate the mass given the same net force here. So I have 3 times 24.0 meters per second squared, which will give me 72.0 meters per second squared. So I was doing that without looking at my notes. So then we can also have a question where we have to kind of combine them, where we put them together. So in this case, we want to know what the new acceleration is going to be if the net force decreases by a factor of 2. So this is a direct relationship. So acceleration is directly related to F net. So if I divide my F net by 2, I divide my acceleration by 2. Okay. So this change here will give me a new acceleration of 24. I'm always going back to the original acceleration that I was given in the beginning of the problem. So 24 meters per second squared divided by 2, which will give me 12.0 meters per second squared. So that takes care of the net force changing by a factor of 2. The other change I'm going to make here now is the mass increases by a factor of 4. So I have mass increasing by a factor of 4. Just putting that there. So mass is going to become 4 times mass. And remember, acceleration is inversely proportional to mass. So my acceleration, right, I'm taking on the right-hand side, mass is becoming 4 times as big, but then what has to happen to the acceleration is that means the acceleration has to be divided by 4. So my acceleration nu is going to equal 1/4 of my acceleration that I found here, because I'm doing this in 2 steps. I could have done this in 1 step. So that makes my new acceleration 3 meters per second squared. That decrease in the net force and an increase in the mass both caused a decrease in the acceleration. Okay. Again, I'm going to change the slide here, but you can pause it if you're not caught up. Okay. And the other thing about this too is we can talk a little bit more about this on Monday if this example 3 is causing a little bit of trouble. It usually does. It's not as straightforward as plugging numbers into a formula. It's a little bit of a different kind of way of thinking. It's that higher mental activity. Okay, and so then the thing I also want to talk about here is getting into gravity a little bit, the force of gravity and the normal force. And so to talk about the force of gravity, we have to talk about some definitions of some words here. And so we have to look at what weight means, what mass means, and what acceleration due to gravity then is. Okay. So the formula that relates these here is acceleration due to gravity is equal to the force of gravity divided by mass, where g is acceleration due to gravity, which we've already seen in the first unit. Okay, and so that's 9.81 meters per second squared. Fg is the force of gravity in newtons. It's also called weight. And m is mass, again, which we should be familiar with, and that's in kilograms. So mass, which is given the variable m, it's measured in kilograms. It is a measure of how much matter is in an object. It's a scalar, and it remains constant no matter where you are. So wherever you are in the universe, mass is constant. Your mass is the same on Earth as it is on the Moon, as it would be on Mars, as it would be if you're floating around in the middle of space. Weight, on the other hand, weight is measured in newtons. Which is an N, right? Weight is the force due to gravity. Okay? It's a measure of the force of gravity on an object. And its value depends on where you are located in the universe. It depends on g, right? It's a vector quantity, so it has a direction. It's always down. Acceleration due to gravity is measured in meters per second squared, because it's an acceleration. It determines an object's weight. Which is the force due to gravity. These should have vector symbols on here. It changes depending on your proximity, or it changes depending on the proximity to a large body. So something like the Earth or the Moon. Okay. So all objects that are within the same area are going to experience the same acceleration due to gravity. Everything that's close to Earth experiences an acceleration due to gravity of 9.81 meters per second squared. And it is a vector quantity. It acts down all the time. So notice that this is a similar formula. This formula here has the exact same setup as the formula for Newton's second law. Right? Acceleration is equal to a force divided by mass. So if we want to determine the weight of a 16.7 kilogram object near Earth's surface, that means we're looking to find weight, we're looking to find force of gravity. Okay? We have the mass, which is 16.7 kilograms. We have the acceleration due to gravity, which is 9.81 meters per second squared, and we're simply going to plug that into the formula. Now I've been rearranging that, right? This is G is equal to Fg over m. To get Fg by itself, I'm basically just cross multiplying the mass and the acceleration due to gravity. So 16.7 kilograms times 9.81 meters per second squared, and that equals 164 newtons down. Find the acceleration due to gravity near planet X if a 125 kilogram object has a weight of 579 newtons. We want to know what G is. We're looking for the acceleration due to gravity. We have a mass of 125 kilograms, and it has a weight, which is the force due to gravity, of 579 newtons. So G is equal to Fg over m, which is 579 newtons, divided by 125 kilograms, which is 4.63 meters per second squared. And again, G always acts down. Okay, and I'm going to move the page ahead, but you can pause it as much as you need to catch up. So just talking about the normal force again, which we discussed a little bit on Wednesday. The normal force, remember, is a force of support. So it's a force of support, and it exists even if the object is moving, but it only exists on objects that are sitting on a surface. So an object has to be on a surface in order for it to experience a normal force. So it must be on a surface. So a falling body, which is what we call any kind of projectile that's moving through the air, doesn't experience a normal force. So all surfaces exert a force of support on any object placed on that surface, and that's called the normal force. This force of support exists even if the object's moving. And when we're talking about a horizontal surface, so something like a table, and if we just have an object sitting on a table, then the force of gravity that's acting down on that object is equal to the normal force that's acting up. And we sort of established that already when we're working with net force. Fg and Fn were equal. So as long as you are on a horizontal surface, Fn is simply equal to Fg, which is mg. Okay? And this is provided there are no other vertical forces. If there's other vertical forces, that's different, and we'll talk about that in one of our examples. So, and this is really important. Objects that are not on a surface do not experience a normal force. Okay, so if it's not sitting on a surface, there's no normal force there. So just a couple quick examples here. A 9.8 kilogram object rests on a surface. What is the normal force acting on the object? Oh, and to go back up here, this relationship here is not on the formula sheet. So that's something you have to remember from doing free body diagrams of objects sitting on a surface. Right? If we have an object here for part A that's on a surface, it has a force of gravity acting down on it, and it's going to have a normal force acting up on it. So the normal force is equal to the force of gravity, which is m times g, which is equal to 9.8 kilograms times 9.81 meters per second squared, which gives us a normal force of 96 newtons, and that acts up. If we sort of change the situation a little bit, so now what we have is we still have the object sitting on the surface, okay? And it has a force of gravity acting down on it. That force of gravity hasn't changed, right? The force of gravity, that's a constant based on the mass of the object, as long as the object is still within the vicinity of Earth. So this is still 96 newtons, is that force of gravity, because we found that this is that same thing there. But now we're saying we've also got an applied force. We're applying a force, we're pushing down on the object and applying a force, F applied, equal to 35 newtons. Okay, so that means, and the object still isn't moving. Like we're thinking about this object sitting on a surface. If it has a normal force, we're pushing down on it. It's not moving. So think about pushing something down on a table. It doesn't move through the table. But what happens now is that table has to function a little bit more to support much more than just the force of gravity acting down on the object. It has to support the force of gravity acting down on the object as well as that extra force that you're applying to it. So that normal force then will be the sum of those two forces. So we're still working with the fact here that this is a net force of 0 because it's not working. So I can write this way. F net equals Fn plus Fg plus F applied. Okay. Where if it's, I'm stationary, the object is stationary. It's not moving. So then it has an F net equal to 0. Okay, so that's still true. We still have balanced forces here. The forces are balanced. And I'm going to make down negative and up positive. So F net is 0. Fn we don't know. But Fg is negative 96 newtons. And F applied is negative 35 newtons. So that when I solve this, I get that Fn is equal to 96 newtons plus 35 newtons, which will give me a normal force of 131 newtons, or with proper sig figs, 1.3 times 10 to the 2 newtons up. So I can change the normal force, the force of support, by exerting a force down, even though I'm not moving the object. Okay, and that takes care of that lesson. And your assignment then, what I would like you to work on for the rest of the class, and then for practice over the weekend in preparation for Monday's class, is page 71 to 76 in your work booklet, and it's numbers 1 to 16. Have a good weekend, you guys. See you on Monday.